Hello friends, today we are going to revise a new chapter known as electrochemistry. Electrochemistry, it is the area of chemistry which deals with the interconversion of electrical energy and chemical energy. Suppose there are two metal rods, and they are connected to each other via a wire. Suppose there are two metal rods, they are connected to each other via a wire. And suppose they are dipped in an electrolytic solution. Suppose the electrolytic solution is NaCl. Then these metal rods are known as electrodes. These are known as electrodes. And this is an electrolytic solution. Okay. So the electrode at which oxidation takes place is called anode. So at anode, oxidation takes place. And at cathode, reduction takes place. Remember this, at anode, oxidation takes place, and at cathode, reduction takes place. So therefore, at anode, the reaction looks somewhat like this. Cl negative, because the electrolytic is MCl, our electrolytic solution is our MCl. So Cl negative goes to half Cl2 plus. Since oxidation is taking place, therefore ejection of an electron from Cl negative is taking place. And at cathode, the reaction looks somewhat like this. NCl M plus electron gives. Okay, now electrolysis. Let's come to electrolysis. Electrolysis, it is a process of chemical decomposition of the electrolyte by the passage of electric current. Suppose an electric current is passed through an electrolyte, therefore decomposition of that particular species start taking place. And it is carried out in a cell called as electrolytic cell. So, in case of electrolysis, let's discuss electrolysis. This process is governed by several laws, just like thermodynamics, and we call it as first law of electrolysis or the second law of electrolysis. Well, they all are clubbed together, and they are known as Faraday's laws of electrolysis. Faraday's laws of electrolysis. So the first law of electrolysis says that first law of electrolysis says that the amount of any substance deposited or dissolved at a particular electrode is proportional to quantity of electricity that is utilized. Okay, so remember, here it is not the electricity that is passed. We are saying that the amount of electricity is utilized. Okay, so the first law of electrolysis is saying that amount of any substance, that is W, deposited or dissolved at a particular electrode is proportional to the quantity of electricity utilized, that is charge. Okay, so we know that Q equals I into T. Therefore, W equals W is directly proportional to the product of current that is passed for a T amount of time. Okay, so putting the constant of proportionality here, we get the expression as W equals ZI, where W is the mass of substance deposited or liberated, Q is the amount of charge utilized in coulombs, okay, not passed, remember, and current, I is the current in amperes times the time for which current flows through the cell in seconds, and Z is the electrochemical equivalent. Z is the electrochemical Chemical equivalent. Okay. Now, electrochemical equivalent, by definition, it is the mass of substance deposited in gram either by passing 1 coulomb of charge or by passing 1 ampere of current for 1 second. It can be verified if we keep I equals 1 ampere, T equals 1 second, the W will be equal to Z, and hence we can say that it is the amount of charge deposited, amount of substance deposited in gram either by passing 1 coulomb of charge or by passing 1 ampere of current for 1 second. Okay. Now, 1 Faraday, it is the quantity of charge carried by 1 mole of electron. So, it is the quantity of charge carried by 1 mole of electron. So, 1 mole of electron is 6.023 into 10 raised to the power 23. And the charge multiplied by the charge carried by 1 electron. So, charge carried by 1 electron is 1.6 into 10 raised to the power minus 19 coulomb. So, 1 Faraday is 96500 coulomb. This value is approximate, remember. So, therefore, we can say that 1 Faraday is the quantity of charge which must be passed in order to deposit or dissolve 1 gram equivalent of any substance. Okay. Now, remember, if E is the equivalent mass of a substance, then E into Z equals 96500. So from here we get the value of Z as E upon 96500. So the value of chemical equivalent, electrochemical equivalent for a particular species with equivalent mass as E is E upon 96500, and hence this is different for different species. Now, if we substitute the value of Z in first law of electrolysis, we get the expression of amount of substance deposited equals E into I into T upon 96500. Okay. Now, suppose that we know that the value of the formula of density is weight upon volume. Since density equals weight upon volume, therefore weight equals density into volume, right? Hence, we can write W as volume into density equals area into L into density. Volume is just area into length equals E I T upon 96500. So this is the case whenever we consider the electroplating of any metal. Okay, so whenever electroplating of any metal is taking place, this formula needs to be considered, where A is the area to be electroplated and T is the thickness of layer deposited. Okay, and D is nothing but the density of metal deposited. So if we want to electroplate a particular area of value A and we want the thickness to be L, then the amount of charge that need to be passed is I into T, or here if we say that A into L into D equals E upon 96500 into Q. Okay, we know the value of A, we know the value of L, we know the value of D, and we also know the value of E for a particular metal. Therefore, the amount of charge that needs to be carried out is A into L into D into 96500 upon E. So this is the case of electroplating of any metal substance. Okay, So let's come to the second law of second law of electrolysis. Second law of electrolysis. It is nothing but it is the extension of the first law of electrolysis. This law says that the amount of different substances deposited or dissolved by the same quantity of electricity by the same quantity of electricity are proportional to their respective chemical equivalent weights. Okay, so this just says that since we know W equals E into I into T upon 96500, suppose the I amount of electricity, I amount of current is passed for T amount of time through two different metals, and hence we know that I and T, they both are same for both of the metals. So from here we get W is directly proportional to equivalent weight of that particular metal, and hence the amount of metal which will be deposited will be in proportional to its equivalent weight, and from here we can say that W1 upon W2 equals E1 upon E2. This is the second law of electrolysis. It says that the amount of different substances deposited or dissolved by a same quantity of electricity are proportional to their respective chemical equivalent weights. Okay, so let's come to the reduction potential. Now, reduction potential of any electrode is represented by ERP, and if we take this value at standard conditions, then it is represented as E naught RP, where this is the standard condition, standard reduction potential. They are related as if E is the reduction potential at non-standard conditions, then they are related by the formula ERP equals E naught RP minus RT upon NF ln concentration of products divided by concentration of reactants. Okay, so these are related by this formula, and thus it is possible that a cation A positive with lower standard reduction potential getting discharged in preference to cation B positive having higher standard reduction potential, because their concentrations might be such that the reduction potential of A positive is higher than that of B positive. So since they are related by the concentrations, and hence this is possible. Okay, so let's discuss about electrolytic conductance. About electrolytic conductance. Now, Ohm's law, we have already studied about Ohm's law that electric current is directly proportional to the potential difference between any 2 points. Now, Ohm's law, this is valid for metallic conductors, we know that, but it is also valid for electrolytic conductors. Okay. Now, here therefore, in case of electrolytic conductors, R, that is resistance, is directly proportional to L upon A, where L is the length and A is the area of cross section of the solution column held between the electrodes. Okay, so from here we get the value of R equals rho into L upon A, where rho is the resistivity. So the unit of rho unit is ohm meter. The unit of resistance is ohm, the unit of length is meter, unit of area is meter. So from here we get the unit of rho as ohm meter. Now for solutions, it is more convenient to think about conductance rather than resistance. Okay, so for solutions, we should think about conductance. Okay, so conductance, it is denoted by G. It is nothing but the reciprocal of resistance. G equals 1 upon R. So from here it becomes 1 upon rho into A upon L. 1 upon rho is called conductivity. Since rho is resistivity, therefore reciprocal of resistivity is known as conductivity, denoted by kappa. Okay, kappa is 1 upon rho. Kappa is 1 upon rho, and the unit of conductivity, its unit its unit is Siemens per liter. Siemens per meter, because since the unit of resistivity is ohm meter, and per ohm is known as Siemens. Per ohm is known as Siemens. So the unit of resistivity of kappa is Siemens per meter, and unit of conductance is Siemens. Okay. Now equivalent conductivity is of an electrolyte in solution. Let's discuss about equivalent conductivity. Equivalent conductivity. Okay. Now equivalent conductivity of an electrolyte in solution, the conductivity powers of all ions furnished by one equivalent of electrolyte in any solution. Okay, so I repeat it again, that the conducting power of all the ions furnished by one equivalent of an electrolyte in any solution is termed as its equivalent conductivity. It is denoted by lambda, capital lambda. This is known as capital lambda EQ. Okay, which in this case capital lambda EQ equals conductivity upon normality of that particular electrolyte or particular electrolytic solution. Okay, and there is another term known as molar conductivity. Molar conductivity. This this is the same as equivalent conductivity, but in this case, in molar conductivity case, this is the conductivity power of all the ions furnished by 1 mole of an electrolyte in any solution. Okay, it is denoted by lambda m, which is equal to molar conductivity. Lambda m is equal to kappa upon molarity of that particular electrolytic solution. Now since molarity into n factor equals normality, therefore we get the value of molar conductivity equals equivalent conductivity into n factor. Okay. Now in case of any compound or in case of any electrolytic solution, we do not generally get one particular ion. Therefore we get a group of ions, and hence the behavior of that particular solution, the conductivity of that particular solution is governed by Colrausch law. This is governed by Colrausch . Now, it states that at infinite dilution, the molar conductivity of an electrolyte can be expressed as the sum of contributions from its individual ions, and hence by mathematical formula. In case of Colruy's law, here infinite sign is used to denote that we are considering infinite dilution. M is the molar conductivity equals mu positive small lambda. Now, the conductivity or the molar conductivity of one particular ion we denote it by small lambda. It says that now this plus mu negative lambda negative. So this is the mathematical form of Colruy's law, where nu is the stoichiometric or the number of atoms in a particular compound, and here positive sign is used for cations, negative sign is used for anions. Now suppose for example, lambda HCl at infinite dilution will be mu of H plus lambda H plus at infinite dilution plus mu negative lambda Cl negative at infinite dilution. So from here, since nu H plus is 1, Cl negative is 1, therefore it comes out to be H plus plus lambda Cl negative plus. Okay. Here is another example. At infinite dilution, molar conductivity of MgCl2 will be equal to lambda Mg2 positive at infinite dilution, because the nu for Mg2 positive is 1, and since nu for Cl negative is 2, therefore here 2 will come as a coefficient. Okay. So now there are different types of cells we deal in this chapter. Now let's consider one important cell known as electrochemical cell. Electrochemical cell. Electrochemical cell. By definition, they are the cells in which chemical energy is transformed into electrical energy. This means that chemical reactions produce electric current. Therefore, we discuss this part of the chapter separately, or this type of cell separately. Now, the behavior of that particular cell is governed by Nernst Equation. That is, the amount of electrical energy that will be produced by that particular cell is given by Nernst Equation. So let's discuss Nernst Equation in that. To write here electrochemical cell, that here chemical reactions produce electrical energy. So now, Nernst equation, it is used to relate either half cell potential or EMF of cell with the concentration of involved species. Suppose in electrolyte this reaction is taking place, XA plus YB ZC plus WD. Okay, now suppose this reaction is taking place, therefore we know that since G equals G naught plus RT ln K in case of any reaction, therefore in this case X into GA for the species A will be equal to X into GA naught plus RT ln A raised to the power X. Similarly, Y into GB equals Y into G naught B plus RT ln concentration of P to the power Y. Z into GC equals Z into G naught C plus RT ln CZ, and W GD equals W into G naught D plus RT ln D to the power W. Okay, now if we rearrange these four expressions, we get the value of delta G for that particular reaction equals delta G R naught plus RT ln C to the power Z D to the power W upon A to the power X B to the power Y. This is nothing but the equilibrium constant for this particular reaction. Okay, so the value of equilibrium constant, the expression for equilibrium constant in relation with delta G is derived from electrochemistry, as you will be seeing, or you already must have seen in your regular chapters. So now, in case of any spontaneous reaction occurring in a cell occurs with a decrease in free energy, and we already know this. Therefore, since decrease in free energy is taking place, therefore minus delta G equals total charge into EMF of cell. Okay, now total charge is, since total charge is N into F and EMF of cell is E, so this equals minus delta G. So from here, delta G equals minus NFE, that particular cell. Okay, so and since we are dealing with cell, we are going to write here E cell. Fine. Now if we substitute this expression in this expression, eventually we are going to get the value of E cell equals E naught cell minus RT upon NF ln concentration of C, Z concentration of D to the power W upon concentration of A to the power X concentration of B to the power Y. Okay, now if we substitute the value of constants, that is R equals 8.314 joule per mole per Kelvin, F equals 96500 Coulomb, and if we consider the temperature at 298 Kelvin, that is at room temperature, then from here the value of E cell comes out to be E naught cell minus 0.059 upon N log of concentration of C to the power Z, concentration of D to the power W, concentration of A to the power X, and concentration of B to the power Y. Now at equilibrium, since delta G equals 0, so from here E of cell equals 0. So therefore at equilibrium, E naught cell becomes RT upon NF ln K equivalent. So this is nothing but the equilibrium constant. Therefore E naught cell becomes RT upon NF ln K equilibrium. So remember this formula. Okay, so since from here delta G naught equals minus RT ln K equilibrium. Now there are many other types of cells. So, for example, concentration cells. In case of concentration cells, E naught of cell equals 0. Remember this. In case of concentration cell, E naught of cell equals 0. Now, in case of concentration cells also, there are many types known as electrode concentration cells or electrolyte concentration cells. Now, and then we discuss and then we study in this chapter about batteries. Batteries are nothing but the series of combined electrochemical cells. And batteries are also divided into several parts known as primary batteries, secondary batteries, and they are further divided as dry cell battery, nickel cadmium battery, mercuric battery, fuel cells battery, or lead storage battery. So these were the concepts that were essential for our revision purposes, and as far as further theory is concerned, that is to battery, that concentration cells, you must have gone through your books. Okay, so let's discuss some of the questions after discussing this. Now, the first question says that the EMF of a cell, and cell is represented like this: AgCl saturated solution, Cl negative, whose concentration is C1, to AgCl at 298 Kelvin is given by. Now there are 4 options, out of which only one is correct. So let's calculate what is the EMF of this particular cell. Okay, now the given cell, whatever cell that we are given here, this cell, it can be reduced. So let's reduce this cell. The given cell, it can be reduced to AgCl, whose saturated solution are there. Saturated solution is there. Ag positive, its concentration is Ksp upon Cl negative by Ag. So this is the cell in reduced form, or in more simpler form. Now we know that at anode and at cathode, oxidation and reduction take place respectively. Therefore, at anode, Ag gets reduced to Ag positive at anode, plus electron is ejected out. And at cathode, Ag positive at cathode gets reduced to Ag, and this electron is accepted by this Ag cathode. Therefore, here electron is accepted. We can write here, or in more simpler form, we can write this reaction as reduced to Ag. Okay, now since this is a concentration cell, okay, you can easily see this is a concentration cell, Ag. Therefore, E naught cell here equals 0 for this concentration cell, and hence E cell equals 0.059 log of Aga positive upon Ag positive. Aga is the concentration of silver at anode, and Ag is concentration of silver at cathode, and here it will come negative sign because of this expression, since E naught cell is 0, and hence the value of E cell will be minus 0.059 upon n log of this, and n equals 1 here. Only one mole of electron is accepted or ejected at cathode or anode. So hence E cell equals minus 0.059 log of Aga positive upon log of Agc positive. Now therefore E cell, since log we can rearrange it, so we get the value of E cell as 0.059 log Agc positive upon Aga positive. So this is the value of E cell that we have obtained so far. Now there is nothing left, just accept substitution of values. So let's substitute the values here. 0.059 log of Ksp upon Cl negative under root Ksp. Okay, so this is the concentration of AgC positive and this is the concentration of AgA positive. So from here the value of E cell is 0.059 log under root Ksp upon EL negative. Okay, it comes out to be 0.059 log Ksp upon C1. So this is the correct answer. Let's see which one of the options correspond to this answer. This answer is C. Okay. Okay, so let's discuss another question. The question says that the electrolysis of dilute aqueous NaCl solution was carried out by passing 10 milliampere current. Okay. Now the time required to liberate 0.01 mole of H2 gas at the cathode is. Now they are asking us the time that is required to liberate 0.01 mole of H2 gas at cathode. Okay. Now we know that from that Q equals I into T. Since Q equals I into T, right? So therefore, from here the value of Q is 10 into 10 raised to the power minus 3, since 10 milliampere current is passed out, into 10 and into time, that is T. So from here value of Q is 10 raised to the power minus 2 into T. Now let's see what is the reaction that is taking place here. The reaction is 2H2O plus 2 electron giving us H2 plus 2OH negative. Okay, so from here to liberate 0.01 mole of H2, 0.02 Faraday charge is required. Okay, now since to liberate 1 mole of H2, 2 Faraday charge is required, and hence to liberate 0.01 mole of H2, 0.02 Faraday charge is required. So therefore Q equals 0.02 into 1 Faraday or from here the value of Q comes out to be 0.02 into 96500 coulomb. Okay, now this charge will be equal to this charge and hence 10 raised to the power minus 2 T equals 0.02 into 96500. So from here value of T comes out to be 19.30 into 10 raised to the power 4 seconds. Okay, so therefore the time required to liberate 0.01 mole of H2 gas at cathode is 19.3 into 10 raised to the power 4 seconds. So this is the answer for this question. Okay, let's move to another question. The question says find the equilibrium constant for the reaction In2 positive plus Cu2 positive gives In3 positive plus Cu positive at 298 Kelvin. Okay, now the given condition is E naught Cu2 positive to Cu is 0.15 volt. E naught In3 positive to In is minus 0.42 volt. E naught In2 positive to In is minus 0.40 volt. So let's see how to solve this question. Now if we write the expressions here, if we write the reactions, so we get the reaction as In3 positive plus 2 electron gives In positive. It has got certain delta G value, so let's denote it as G1. And E naught is given to us as minus 0.42. Okay, now In2 positive plus electron gives In positive. It has got certain delta G naught value, let's note it as delta G2, and E naught as minus 0.40. Okay, so now let's subtract equation 1, let's call it as equation 1, call it as equation 2. Now let's subtract equation 1 from equation 2. It will look like this: equation 1 from equation 2. Okay, so we get ion 2 positive, giving us ion 3 positive plus electron. Okay, so suppose it has got a delta G value of delta G and E naught as E naught. Okay, so from here, since delta G is additive, therefore delta G will be delta G2 minus delta G1, delta G2 minus delta G1, since we are subtracting equation 1 from equation 2. Therefore delta G will also get subtracted from delta G2 minus delta G1. Okay, so hence we get, if we equate certain values, we get delta G as minus 1 into F into E naught equals minus 2 into F into minus 0.42 plus 1 into F into minus 0.40. Okay, so from here value of E naught equals minus 2 into 0.42 plus 0.40 equals minus 0.44 volt. Okay, now we are required to calculate equilibrium constant for the reaction In 2 positive plus Cu 2 positive, giving us In 3 positive plus Cu positive. Okay, now in this case, since E naught equals, we are given with the E naught Cu2 positive Cu, E naught Cu2 positive Cu minus E naught that we have considered here, that we have calculated here, this E naught for this particular reaction, this reaction In2 positive to In3 positive. Okay, so In2 positive to In3 positive. So this species is getting reduced, this species is getting oxidized. So from here value of E naught comes out to be 0.15 minus this minus 0.44. It is equal to 0.59 volt. Okay, now since minus NF E naught equals minus RT ln K, so from here 0.59 upon 0.059 equals ln K. So from here we get the value of K as 10 raised to the power 10 units. Okay, so this is the required answer for us, and this question was asked in IIT JEE 2004. Okay, now let's discuss another question. The question says that if the pressure of H2 gas is increased from 1 atm to 100 atm, keeping H plus concentration constant at 1 molar, the change in reduction potential of hydrogen half cell at 25 degrees Celsius will be, there are 4 options: 0.059 volt, 0.59 volt, 0.0295 volt, or 0.188 volt. Okay, so let's discuss what is there in this problem. So let's write first the half cell reaction for hydrogen half cell acting as cathode. So half cell reaction for hydrogen half cell active as cathode is 2H plus 2E negative, giving us H2. Okay, now therefore EH plus 2H2 equals E naught H plus 2H2 minus 0.059 upon 2 log pressure due to H2 upon H plus squared. Now since this is a concentration cell, therefore this quantity will be 0, and hence from here we get the value of E H plus 2H2 as minus 0.059 upon 2 ln H2 upon H plus squared. Okay, so from here we get the value of E H plus H2 as minus 0.059 upon 2 log. Oh, here it is log, it's not ln. So this value will be equal to 1 upon H plus squared. So this is the initial value of E H plus by H2 when the pressure of H2 gas was 1 atm. Now suppose this is equation 1. Now if the pressure of H2 gas is 100 atm, then value of E H plus H2 equals minus 0.059 upon 2 log log 100 atm upon H plus ion concentration. This is because concentration of H plus ions is same, it has not been changed. So this is, suppose it is the second equation. Okay, now when the pressure of gas is changed to 100 atm without changing H plus, the reduction potential is this. Therefore change in reduction potential, suppose this is E dash. Now the change in reduction potential, therefore change in reduction potential equals E H plus H2 minus E dash H plus H2. So from here we get the value of delta E H plus H2 as 0.059 upon 2 log of 100 upon H plus squared into H plus squared upon 1. We have just used the property of logarithms. So from here the value of delta E H plus H2 is 0.059 upon 2 into 2. This comes out to be 0.059 volt. This is the change in reduction potential of this particular species when the pressure is increased to 100 atm from 1 atm. So this question was also asked in IIT JEE. Okay, so now let's discuss another question. The question says that find the solubility product of a saturated solution of Ag2Cr2O4 in water at 298 Kelvin if the EMF of the cell Ag positive saturated in Ag2Cr2O4 solution gives Ag positive having concentration as 0.1 molar Ag is 0.164 volt at 298 Kelvin. So the cell is given to us like this. Cell construction is like this. So let's see how to approach this problem. Now for a given cell, the reaction occurring at anode and cathode arc. So first let's write down the half cell reactions. At anode, the reaction is Ag to Ag positive at anode plus electron. Now at cathode, reaction is AgC positive plus electron giving us Ag. Okay, so therefore net cell reaction is Ag cathode giving us Ag at anode. Okay, now therefore, since this is the case, hence we can say that it is an electrolyte concentration cell with E naught equals 0. Okay, now since E naught cell equals 0, because this is a concentration cell, therefore E cell equals minus 0.059 upon 1, because only one electron transfer is taking place. 1 log of Ag at anode upon Ag at cathode, concentration of products upon concentration of reactant. Here we are considering product is Ag at anode and reactant is Ag at cathode. So from here the value of E cell comes out to be 0.059 upon 1 log of Ag at cathode upon Ag at anode. Okay, now the anode compartment has saturated solution of Ag2CrO4. It has got the saturated solution of this species. It is supplying Ag positive ion concentration. Okay, now let the solubility of Ag2CrO4 be X moles per liter. If the solubility of Ag2CrO4 be X moles per liter, therefore Ag2CrO4, this particular reaction at equilibrium, we can say that since this is solid, we are not going to consider its concentration, and hence at equilibrium it is 2x and it is x. Therefore Ksp equals Ag squared CrO4 to negative. So from here it comes out to be 2x squared into x equals 4x cubed. Okay. Now since Ksp equals 4x cubed, so from here value of x equals Ksp upon 4 to the power 1 upon 3. Okay. So from here the value of Ag positive equals 2x equals 2 into Ksp upon 4 to the power 1 by 3. Now since E cell equals 0.164 volt, it is given in the question. Now this equals 0.164 equals 0.059 upon 1 log 0.1 upon, because here the concentration of cathode compartment is 0.1 molar. This is already given in the question. So at 298 Kelvin it is 0.059 upon 1 log of 0.1 upon 2 into Ksp upon 4 to the power 1 by 3. So therefore Ksp equals, if we simplify it, if we solve it further, we get the value of Ksp as 2.24 into 10 raised to the power minus 12 molar cubed. Okay. So this was the answer of this question. Now let's discuss another question. The question says that in acidic solution of copper 2 plus salt containing 0.4 gram of Cu2 plus is electrolyzed until all the Cu is deposited. The electrolysis is continued for 7 more minutes with the volume of solution kept at 100 milliliter and the current at 1.2 ampere. Calculate the volume of gases evolved at NTP during entire electrolysis. Okay, so the acidic solution of copper Cu2 plus is containing 0.4 gram of Cu2 plus is electrolyzed. Now, in this case, it is not mentioned about the acidic salt of Cu2 positive. Okay, now since it is not mentioned about the acidic salt, we have to assume it and then we'll have to solve it for two different conditions. Okay. Now, by acidic salt of Cu2 positive, we mean that the kind of acidic salt is this. What kind of acidic salt is this? Does the acidic salt have chloride, sulfate or nitrate as anion against the cation? And the answer will solely depend on the assumption we make in the beginning about the acidic salt. Therefore, first let's assume that the salt is of cupric chloride. So first, let's assume the salt is CuCl2, cupric chloride. Okay, now in the first part of electrolysis, the reactions occurring at the two electrodes are, now at cathode, the reaction occurring is Cu2 positive plus 2 electron giving us Cu, and at anode this is 2Cl negative giving us Cl2 plus 2 electrons. Okay, now the reaction occurring at anode is oxidation of chloride in preference to OH negative, since the standard oxidation potential of Cl negative is greater than OH negative. Okay, now therefore the moles of Cu2 positive reduced at cathode is, now moles of Cu2 positive reduced at cathode is equals 0.4 upon 63.5, because 0.4 gram of mass is given and 63.5 gram per mole is the atomic weight of Cu. Now therefore the moles of electron required at cathode, since 2 electron is required for 1 Cu2 positive ions, therefore moles of electron required at cathode equals 2 into 0.4 upon 63.5. This is also equal to the moles of electron released at anode, since the whatever mole of electron is required at cathode is the released at anode. So this is also equal to moles of electrons, released at anode. Okay, now therefore moles of Cl2 liberated at anode is, therefore moles of Cl2 liberated at anode equals 2 into 0.4 upon 63.5. Since 1 mole of Cl2 is liberated by using 2 moles of electron, therefore its value will be half. Okay, so hence we will half that particular value. So from here its value come out to be 0.4 upon 63.5. This is the number of moles that will be liberated at anode of Cl2. Now, hence volume of Cl2 liberated at STP at anode is, we know that 1 mole of a gas liberate 22,400 milliliter at STP, that is 22.4 liter at STP. Therefore, this amount of mole will liberate, hence volume of Cl2 liberated at STP at anode equals 0.4 upon 63.5 into 22,400 milliliter. It comes out to be, if we solve it, we get 141 milliliter. Now in the second part of electrolysis, when current is passed for 7 more minutes, okay, now in second part of electrolysis, when current is passed, for 7 more minutes, now then the H plus will be reduced at cathode, since Cu2 positive ions are discharged completely and OH negative ions are oxidized at anode, since Cl negative is also completely oxidized. Hence the reactions occurring are, in this case at cathode, the reactions occurring are 2H plus 2E negative giving us H2, and at anode it is 2OH negative plus 2OH negative giving us H2O plus half O2 plus 2 electrons. Okay, now therefore moles of electron passed, moles of electrons passed equals 1.2 into 7 into 60 upon 96500. For 7 more minutes, this is 7 into 60 equals seconds. 7 into 60 seconds, 7 minutes mean. So the volume of H2 at STP released at cathode, hence volume of H2 at STP released at cathode equals 1.2 into 7 into 60 divided by 96500 into 22400 equals 58.49 milliliter. And the volume of O2 at STP released at anode is, now volume of O2 at STP released at anode equals 1.2 into 7 into 60 divided by 96500 will divide it by 4 further, because the volume of O2 is further half than that of H2, equals into 22400 equals 29.245 milliliter. Okay, so therefore total volume of gases Cl2 plus O2 plus H2 liberated at STP during entire electrolysis. During entire electrolysis is volume of H2 plus volume of O2 plus volume of Cl2. It comes out to be 58.49 milliliter plus 29.245 milliliter plus 141 milliliter, because volume of O2 released is 29.245 milliliter, volume of H2 at STP released is 58.49 milliliter, and volume of Cl2 is 141 milliliter. So therefore total volume total volume equals 228.735 milliliter. So this is the case when we had assumed that the salt is CuCl2. Now let's assume that the salt is CuSO4, then what will be the volume liberated? Now in the first part of electrolysis, the ions discharged at cathode and anode are Cu2 plus and OH respectively. Now in this case, it is recommended that you solve this question yourself, but the only trick in this part is this. Now let's assume the salt is CuSO4. Okay, now just solve this question yourself. Every process is similar to that of the previous parts process, but remember that in this case the ions discharged at cathode and anode are Cu2 plus and OH negative respectively, because here since the ions discharged was Cl2, because the oxidation potential of Cl is greater than that of OH negative. But in case of CuSO4, oxidation potential of SO4 2 negative is smaller than that of OH negative, and hence at anode OH negative will be released. Okay, and hence at anode OH negative will be released. Okay, so solve this question yourself, and I must tell you that the answer for this question will be total volume will be 158.285 milliliter. Okay, so because in this case volume of O2 at anode will be 70.55 milliliter at STP, and volume of H2 at STP released at cathode will be 58.49 milliliter, and further volume of O2 at STP released will be 29.245 milliliter. Okay, so solve this question yourself. The answer should come out to 158.285 milliliter. Please go through it. This is a very good problem. Now let's discuss another question. The question says that calculate delta G or reaction of the following reaction. Okay. Now Ag positive in aqueous giving us Cl negative. Ag positive plus Cl negative gives us AgCl solid. Now given the heat of delta G of formation of AgCl is minus 109 kilojoule per mole. Delta G naught formation of Cl negative is minus 129 kilojoule per mole. Delta G naught of formation of Ag positive, here it is formation of Ag positive 77 kilojoule per mole. Now represent the above reaction in the form of cell. Calculate E naught of the cell. Find log 10 Ksp of AgCl. Okay. So now the cell reaction in this case, we can say that cell reactions are Ag plus half Cl2 giving us AgCl. This is the first reaction. Ag giving us Ag positive plus 1 electron is liberated. This is the second reaction, and half Cl2 plus electron is giving us Cl negative. This is the third reaction. Now if we do an operation here, that is first minus second minus third, we subtract second and third from that of first, we get the reaction as we get Ag positive plus Cl negative giving us AgCl. Okay, so therefore cell representation, cell representation is Ag, its cell representation is Ag positive, AgCl, Cl negative, Cl2. Okay, so this is the cell representation. Now, for this particular reaction, for the reaction like Ag positive, aqueous plus Cl negative, aqueous giving us AgCl solid. Now, delta G equals, delta G, or in standard condition we say that delta G naught equals summation of delta G naught of products P minus summation of delta G naught of reactants. Okay, so the first part of the question, it is asking us to calculate the value of delta GR for the reaction. So the delta G in this case will be, delta G naught in this case will be minus 109 minus 129 plus 77 kilojoule per mole. Okay, or here it comes out to be minus 109 plus 129 minus 77 equals minus 57 kilojoule per mole. Now, since we know that delta G equals N minus NF E naught, therefore, since one electron exchange is taking place, therefore minus 1 into F into E naught equals minus 57. Okay, so from here, the value of, we can say that minus 1 into 96500 into E naught equals minus 57. So from here, value of E naught comes out to be 57. Since the unit is in kilojoule per mole, we'll convert it into joule. 1000 upon 96500. So from here, its value comes out to be 0.59 volts. Okay, so the value of E naught has also been solved. Now, since we know that delta G equals minus RT ln K naught, right? Therefore, minus 57 equals minus 2.303 RT log K naught. So from here, value of log K naught, it comes out to be 57 into 1000 divided by 2.303 into 8.314 into 298. So log K naught is equal to 9.98, or we can take it as 10. So from here, value of K naught comes out to be 10 raised to the power 10. Okay, now since KSP equals 1 upon K naught, now since KSP equals 1 upon K naught, therefore the value of KSP is 10 raised to the power minus 10. So therefore, log of KSP equals minus 10. This is the required value of log KSP in this question. So the question was asking us to calculate delta G, E naught and log 10 KSP of HCl. So delta G is minus 57 kilojoule per mole. Cell representation is this is the cell representation, and value of E naught is 0.59 volt, and log KSP equals minus 10. So this was what asked in this question. Okay, so let's discuss another question, and the question says that the lead storage cell is discharged, with which causes the H2SO4 electrolyte to change from a concentration of 34.6% by weight to one of 27% by weight. Okay. Now the original volume of electrolyte is 1 liter. Calculate the total charge released at anode of the battery. Note that the water is produced by the cell reaction as H2SO4 is used up, and the overall reaction is PbS plus PbO2s giving us plus 2H2SO4 giving us 2 PbSO4 plus 2 H2SO4. So this water is used up. We have to take care of this fact. So let's see how this problem can be solved. Now before the discharge of lead storage battery, mass of solution. Now before discharge, mass of solution equals 1000 into 1.261 equals 1261 gram, because here the density was given to us 1.261 gram per milliliter and the volume is 1 liter. So converting this 1 liter into milliliter, we have got the mass of solution as 1261 gram. Therefore, mass of H2SO4 equals 1261 into 34.6 upon 100, because 34.6% of solution was there, equals 436.3 gram. Okay, now therefore mass of water equals 1261 minus 436.3 equals 824.7 gram. Fine. Now consider the case after the discharge of lead storage battery. Now let the mass of H2O produced as a result of net reaction during discharge is X gram. Okay. Now let the mass of H2O produced as a result of net reaction during discharge is X gram. This is the net reaction. Okay, so as a result of this net reaction during discharge, let the mass of H2O that is produced is X gram. Therefore moles of H2O produced equals X upon 18, and since 2 moles of H2SO4 is consumed to produce 2 moles of H2O, and hence moles of H2SO4 consumed equals X upon 18. Fine. And hence this implies us that mass of H2SO4 consumed equals X upon 18 into molecular weight of H2SO4, which is 98. Now mass of solution after discharge. Now mass of solution after discharge. After discharge equals 1261. Since law of conservation of mass, so the mass of solution, total mass will be constant throughout. Mass of solution equals 1261 minus 98x upon 18, that is the mass of H2SO4, plus mass of water, that is plus x. Now therefore percentage by mass of H2SO4 discharge is, after discharge, now percentage by mass of H2SO4 after discharge equals 27. It is given in the question that after discharge it gets reduced to 27%. Therefore it equals 27 equals mass of H2SO4 left, mass of H2SO4 left upon mass of solution after discharge. After discharge into 100. Okay. So from here we get something like 436.3 minus 98 x upon 18 divided by 1261 minus 98 x upon 18 plus x into 100 giving us 27. So if we solve this question, if we solve this expression further, we get the value of x as 22.59 gram. Okay. Now from this reaction, it is quite evident that the moles of electron exchanged at anode or cathode is 2. And this is also the moles of H2O produced or moles of H2SO4 consumed. Since it is quite evident that the moles of electrons exchanged at anode or cathode is 2, and since 2 moles of H2SO4 is consumed and 2 moles of H2O is formed, and hence we can say that the total number of electrons consumed equals total number of H2O formed or total number of H2SO4 consumed. So from here, moles of electrons reduced at anode. Therefore, moles of electrons released at anode will be equal to the moles of water used. Okay, sorry, moles of water formed. So moles of electron released at anode equals moles of water, moles of H2O formed equals x upon 18, x equals 22.59 equals 22.59 upon 18. Okay, now there hence total charge released at anode, since we know the total number of moles is 22.59 upon 18, therefore total charge released at anode, charge released at anode equals, since 1 mole of electron has got a charge of 96500 coulomb, therefore this much amount of moles of electron will have a charge of 22.59 upon 18 into 96500 coulomb. So if we solve it further, we get the charge as 1.21 into 10 raised to the power 5 coulomb. Okay, so this question, it has been solved here. It was asking us that calculate the total charge released at anode of the battery. So the total charge released at anode as a result of the discharge is 1.21 into 10 raised to the power 5 coulomb. So this question is solved, and that's all for this chapter. See you in the next chapter.